Hello, everyone. So today we're going to be picking up with a last little bit of molecular orbital theory. Specifically, we're going to be talking about energies. So we've built up these very qualitative MO diagrams, and in order to describe the energies of these systems, we've been relatively just ordering the systems. This molecular orbital is higher or lower in energy than this orbital. But here's the issue. We like putting some numbers to things, and we like to know exactly how stable all of these molecular orbitals are. So in order to determine that, we can either continue with a whole bunch more high-level theory, or we can take an aside and give us a benchmark of something to compare to. And for that, nothing substitutes for experiment. So if I want to measure something about the electrons of a system, spectroscopy is a great way to go. So the technique we're specifically going to be looking at is going to be photoelectric spectroscopy. So this is a bit of a mouth name, but generally the idea is going to be if I have molecular orbitals, I can move those electrons by hitting them with a photon. And specifically by using a UV light source of known frequency, I can, and especially a very strong UV light source, I can hit that electron so hard it jumps straight out of the molecule and goes running free. And by measuring the exact amount of kinetic energy, or the velocity of this electron, when it gets knocked loose, I can use this to figure out exactly how tightly it was bound. So this is essentially the molecular orbital version of the photoelectric effect, with most of the same math. So the general idea is I am going to have a photon that's coming with a whole bunch of energy. It goes ahead, hits an electron. A certain amount of that energy is going to be going to getting the electron out of the orbital, and the rest of it just goes straight into translational motion, because you gotta love the first law of thermodynamics, conservation of energy. It's a huge aid right here. So we can describe this mathematically with almost the same exact equation we did before. So if I know the energy of the photon, and I know the energy of the electron, the difference in between these two is going to give me the ionization energy, literally how much energy it takes to remove the electron. And so the ionization energy is going to be a great place to start for analyzing a molecule. Now, one of the things I want to make note is this particular equation has a nu for h nu, so this is the energy of the electron. This is a v for velocity, because apparently we don't have enough variables in physical chemistry. So just make note of when you're looking at this equation, velocity, frequency, very different. But using this, I want to see if I can figure out how to take that ionization energy and turn it into more detailed information about how tightly bound that electron is to my system, or more specifically, the orbital energy. And for that, we can use a fairly intuitive theorem that actually ends up being surprisingly powerful, and that's Koopmans Theorem, which essentially just states that the ionization energy is equal to the orbital energy of the electron ejected. So if I have an electron that I am removing from a molecular orbital, that tells me the depth of the well, how tightly it is bound. And by convention, how tightly it's bound is also telling me a lot about how much that electron is being stabilized. So as long as we say that the zero in energy for an orbital is the free electron, then this is actually a fairly powerful method. But one of the things we have to make note that this particular formalism of the theorem doesn't quite clearly enough state that our ionization energy is positive. I put in energy, remove an electron. Putting in energy is going to be positive, but the electron should be lower in energy to emphasize that it's bound. So thus, the orbital energy of electron in state I is going to be the negative of its ionization energy. So if I know how much energy it takes to remove an electron. The negative form of that is the energy of that electron while it's in the orbital. Now, one of the really important parts of this specific theorem and this general technique is that I go ahead and shoot a molecule with a set of photons of a given wavelength. Well, I'm not just going to be getting one electron out because there isn't just one MO. I'm going to get a whole bunch of different electrons out, each with their own characteristic velocity, which means each has their own characteristic ionization energy. So this means that I can go ahead and determine the molecular orbital energy of every available MO. Now, here becomes part of the trick, because I need to have a light source with enough energy to remove photons that I care about. And that becomes far more tricky than you'd think. And the reason why is because turns out that for most molecules, electrons are often quite stable. So I need a very high energy photon light source in order to get an electron out of a molecule. And I'm talking about tens or more of electron volts. This is very high energy. So I need a high energy source of photons. But more importantly, I need to make sure that my source of photons only has a single wavelength or single frequency or single energy. Because if I'm producing a spectrum of frequencies, this gets a bit messy because I'm going to get a spectrum of velocities right back out. And I need to have a single set of velocities in order to really interpret this data. So I need something that generates a single set of characteristic wavelengths. So it turns out a really good source of that is helium, because helium has no molecule to it, no bonds, no rotations. All it has is electronic energy, and that's it. Which means that if I use electricity to excite helium to the 1s1, 2p1 state, then it's going to want to very quickly fall back down to the ground state. And it turns out that that relaxation has a very characteristic wavelength of about 58 nanometers. This also turns out to be the equivalent of over 21 electron volts. This is plenty of energy to kick out most valence electrons. So if I'm looking at the valence electrons, so my nice frontier molecular orbitals, these are the ones that I often care about because these are my HOMO and LUMO highest. These are my highest energy occupied molecular orbitals. They're the reactive ones. So if these are the molecular orbitals I care about, this is a great technique. But it is worth noting that occasionally what I care about is electrons that are a little bit more tightly bound. So if I care about core electrons, not that valence shell, then I'm going to want to use an X-ray source. And one of the reasons I wanted to bring this up is because it gives us a very unique spectroscopic technique called XPS, X-ray photon electrospectroscopy. So I particularly like this technique, and it is my personal favorite spectroscopic technique, because what this tells you a lot about is in metals, it's going to tell you a lot about the oxidation state of metals and a lot about the coordination environment, because those inner core electrons are going to reflect a little bit more about what's happening close around the system, and a little bit about some of the extra structures. So this is a technique that's way too in-depth for us right now, but hopefully you can learn a little bit more about it in inorganic chemistry. But again, it's one of my favorites. But because what we're mostly caring about now is those bonding and anti-bonding orbitals, let's take a step back to using helium to shoot high energy light at a molecule. So one of the classic versions of this is I'm going to use my helium lamp, which gives us what's called ultraviolet photoelectron spectroscopy, because that photon is in the ultraviolet range. So this is UPS. No, please do not confuse it with the package delivery system, even though you're probably looking for them outside of your door right now. But using UPS, it's possible to tell us about the uh, orbital energy of any of our valence electrons. So let's use this to look at a simple molecule we've been playing around a bit with lately, N2. So N2 is a triple bond species. My frontier orbitals should be the highest in energy is going to be my sigma bond, as we said last time. And my next highest is going to be my 2 pi bondings. So when I shoot my high energy photon, what I can do is end up measuring the ionization energies for the various species. And we're going to see the first peak coming in at about negative 15, coming in at about 15.6. So this corresponds to a orbital energy of negative 15.6. And then the next one at about negative 16.7. So this means that my sigma bonding orbital has an energy of about negative 15.6 eV. And then my second, my 2 pi bonding orbitals has an energy of about negative 16.7. And then my third bonding orbital is going to, which would be my sigma, 1 sigma anti-bonding orbital, is going to have an energy somewhere around negative 18.7. So this guy's a little bit hard to pull off. And essentially, after that point, we're getting a little bit too close to the energy of the photon we're using, and we lose any real resolution. Now, one of the things that probably a lot of you are going, hey, what about this, is going to be these characteristic extra signals coming after this lead peak. So this lead peak is going to be more or less the ionization energy of the photon I care about. But part of the problem is as I excite the system, when I hit it with a photon, the resulting species is probably going to end up in a excited vibrational state, which means I have to put in a little bit more energy to not just excite out the electron, but crank up the vibrational state too. And this gives us what's called fine structure. So again, this first lead peak is telling me all about the ionization energy of the bonding orbital I care, or anti-bonding orbital that I care about. The rest of these peaks is going to tell me a lot about the vibrational structure. So if you want to figure out the orbital energies, look at the first guy. If you want to figure out the bond strengths through bonding constants and vibrational information, much like we did while using the harmonic oscillator, feel free to try and analyze these subsequent peaks. It's going to give you a little bit more of a simplified version of what many of you have done in lab with I2. So with that said, that pretty much brings us to the basics of using photoelectron spectroscopy to figure out orbital energies. These are going to serve as a nice benchmark, as over the next couple of lectures, we're going to try and emulate these numbers by while we try and more accurately determine the energies of a diatomic molecule. So until then, take care, stay healthy.